as I explained before, these are experiments designed to find out how the frequency response behaves at different frequencies, or how the bandwidth varies with different frequencies. And for that, there were experiments with not only single tones and their audibility threshold. In this case, the test signal, which was always tested when it becomes audible. Before we saw it was a single tone, and there was a masker, or if there would be no masker, it would become audible when the energy reaches the threshold in quiet. That's what we saw before. Then it would become audible, and above that it would stay audible, of course. And this would be the same experiment here, same experiment as what we see here with a single tone. This was the first try here. A single tone was set at a frequency close to 1 kilohertz, where the threshold of audibility is somewhat around 0 dB. So here, in fact, it was plus 3 dB. So a single tone had an audibility threshold of 3 dB. And now they added another tone. Oh, I didn't set up the camera correctly yet. Can I see myself? Can't see myself. Maybe I can ask in Zoom if I'm visible now. Now it looks, I think, in the right direction. So it makes sense, but I guess I have to zoom in a little bit. I can't see myself. Is it okay? Okay, I get a kind of positive feedback, I guess. Thanks. And I can continue with that one. Okay. Then this was the audibility threshold of a single tone at 920 Hertz was 3 dB. Now they made the experiment again, but with not a single tone, but they added a second tone, which was 20 Hertz apart. So we have two tones, one at 920 and one at 940 Hertz. And those two tones had the same level, and the level was increased. Both levels were synchronously increased until they together became audible. And now you can say, when the tones are in the same frequency band, they would their energy would go together to influence the vibration of the basilar membrane. So as long as they are in the same frequency region of the auditory system, they would become audible more easily, because now you have doubled the energy or increased the level by 3 dB, the joint level. But what we see here are the levels of the individual tones. So the individual tones now became, as a group together, they became audible already at 0 dB of each of the two tones. That means if you add two tones, their joint level is increasing by 3 dB. And this makes, again, that the threshold of audibility is reached. But with each of the single tones, is a lower needs just a lower level to become audible. Is this clear?
Like, you mean even if they are not individually hearable?
Each individually would not be audible, but if you play them at the same time, yes, was good remark. If you play them at the same time, they help each other to become audible, let's say. So there's no masking because they are at equal levels. So they rather help them each other to become audible. because they are close enough in frequency that this is not, they would not be perceived as independent tones. One at 1 kilohertz and one at 2 kilohertz, they would not, this effect would not be visible, and we'll see that, later. So in the next step of the experiment, they added 2 more tones at 960 and 980 hertz. So the total bandwidth was now 60 hertz from 920 to 980. And the level of the individual tones again was reduced by 3 dB. That means now all 4 tones had together to become audible as a set of, as the whole set of 4 tones. If you add another 4 tones, so they doubled the number, and now the bandwidth goes from 920 to, here you see the bandwidth, 140 hertz is now the total bandwidth. You have 8 tones spaced by 20 hertz, and that means there are 7 gaps of 20 hertz in between. So the total bandwidth of this 8-tone complex is 140 hertz, and the level again decreased by 6 dB. Again, the levels of the individual tones when they jointly were played just needs to be now 6 dB, but just only minus 6 dB to become audible, because they all 8 tones help each other for becoming audible. Now in the next stage, 8 more tones were added. They seem closer here because it's a nonlinear frequency scale. In the next tones, 8 tones were added, so that the total bandwidth is now 300 hertz. But interestingly, the threshold of audibility for the tones doesn't change much. It means these new tones seem to not help in the audibility anymore. It seems like they are out of the bandwidth, so that these added tones can help the first tones. So the last tones here and the first tones here, they would not be, they would be too far away to help each other to become audible, but probably the center 8 would then be the ones which first meet, help getting audible. And so the threshold only goes down very little below these minus 6 dB. And if you add yet another 16 tones, that means double the bandwidth and the number of tones again, this effect is still the same, that the threshold of audibility almost does not increase any further. That means that you can, with this experiment, you can find out at which point adding more tones doesn't help anymore for the audibility, and then the total bandwidth of the point where you don't see the decrease anymore, but where it goes more towards the flat curve, this threshold, depending on the number of tones. This point would then mark the bandwidth where you would say in this frequency regions, the tones are jointly processed on the basilar membrane. And this would be in the range of 140 hertz, what you can see here. Yeah,
I have some questions. Like the first is changing very linearly in the dB scale, like 3 dB, but like it's very weird because like at some point it just stops changing.
Yeah,
and so like why it is like that?
It seems like so if it would be a brick wall filter, let's say an ideal bandpass filter at that frequency region, then any tone which is outside of one specific width would not count anything, would not contribute anything to the audibility of the other tones, because it would be completely independently processed from if there would be a rectangular frequency response, like going up at this frequency and going down at this frequency, then all the tones outside of that region would not contribute anymore to the audibility of the ones which are within the band. And so then it would really abruptly switch to a flat curve. But since we assume and we see that the magnitude responses of the basilar membrane are of course not brick wall characteristic, but have some kind of slopes going down. There is an attenuation so strong that it doesn't decrease much more, but it still decreases a little bit.
You mean the slope is pretty hard?
Relatively steep, but not brick wall characteristics.
Okay. And I have another question. Like if it doesn't depend, like if they're in phase or not? Like,
no, because they have different frequencies, they wouldn't stay in phase anyway. There would be some kind of beating artifacts and things like that anyway.
Yeah.
If we add two tones which are spaced just by 20 hertz, their phases would change over time, all the time. So they would not be in phase or out of phase.
But it will change, like if you see like addition of both of the tones, it should matter like a little bit, because
but it's short. The beating would mean that the total instantaneous amplitude would fluctuate over time. So there would be some time instances where it's high, where it's higher, and some instances where it's lower. That's what you mean, I guess.
Yeah, low frequency, like very low frequency for the beat. But like if we also change the difference between the frequency, like the delta F, we have 20 hertz there.
This could also have some influence, but in general, as long as because it's just the audibility threshold, for that it doesn't matter so much. If it would be how it sounds, how you perceive the sound when it's audible, then of course it would matter quite strongly. But here they were just asking about, do you hear anything? Okay. Because it was at the threshold in quiet. So, and once the participants in these experiments could perceive something, whatever it was, they would say, now I hear something. And then this would be the threshold where they start saying, now I hear something.
Okay. So it has not much to do with the waveforms, but it's more about
the energy, the total energy, let's say, or total power in a certain frequency range. Yes. Yeah. And so you can do these experiments at different frequencies. So this was now around 1 kilohertz, and you can do it with frequencies around 2 kilohertz and so on. And then you would see the bandwidth where you have this corner here, this corner case. This would get wider if you go to higher frequencies, and by that you can get a kind of a curve with bandwidth depending on frequency. So that is one possibility to do this experiment. And on the next slide, it's more a bit illustrated differently, but it's more or less the explanation for the same experiment, where you either show the threshold of audibility depending on the number of test tones, or the total bandwidth, let's say, of this tone complex. The more tones you add, the wider the bandwidth gets, and the lower the threshold of audibility gets. Here is always the level of each tone of the complex, as I said before. So that's why it's going down, because you have 8 tones which all have the same level. The level can be lower than if it would be just a single tone. And that would be the curve. And you see that you have this at different, here they did the experiment not at the threshold in quiet, but with the uniform masking noise. And you have different uniform masking noise levels. And this is what you see here. This would be the previous experiment, just as a graph and not with all the dots. But this would be the bandwidth and the influence of the bandwidth of the tone complex to the audibility threshold. And here, if you have a uniform masking noise with 10 dB intensity, according to this formula, then the total threshold is raised, but the tendency is still the same. And if you increase the uniform masking noise intensity more, then the threshold goes up, but the shape still stays the same. It means now people have to be asked if they hear some tonal thing or something which is not which differs from the noise they heard before. Here is basically exactly the same experiment, just described differently. Here they don't show the level of each of the individual tones, but the overall level of the test tones, which were always grouped together. And there you see that at the beginning, the level stays constant. It means if you have two tones, the two tones together have twice the power within the frequency region, and that's why it goes when the total power of these two tones is the same as the total power of one tone before, then it would become audible. And if you add two more tones, they can have a lower level, but if the four tones together have the same power as the one tone before or the two tones before, then it becomes audible, and so on. And if you increase the bandwidth, you would add more power with the new tones which are outside of that frequency region, and the total power at the threshold would increase because you have some tones which don't help for reaching the threshold of audibility. And that's why you get, in this case, this curve here. It's basically the same, the results from the same experiment, but just here plotted as the levels of the individual tones, and here the sum of all the tones. If you measure the power of the sum of all tones, then this would stay constant, and then it would just increase once this corner frequency is reached. And they write it, denote this as delta FG, delta because it's the bandwidth, delta F, and G, this was for grouping where tones are more or less grouped together or working together as a group to become audible, and the other tones would not contribute that to that anymore. So this is one a bit complicated to explain, I guess, the one experiment, but which shows that the selectivity of the auditory system can be connected to a kind of a bandwidth. And in order to verify if that gives reasonable results, people did additional experiments. So this was the first one I want to show. There are even more in the literature, but I just picked a few of them to explain what was done to find the frequency resolution of the auditory system. And here, this experiment, the results are from the test tone at 2 kilohertz, and it again uses masking effects. There was a masking signal which contained 2 narrowband noise signals, as you can see here. That's kind of a schematic explanation of the spectrum of the signal in this test. You have one masker which contains of these 2 noise narrowband signals because it's frequency, and this would be the level. And in the middle of this gap between the 2 narrowband noise maskers, there is a test tone. And this would be varied in its amplitude or in its level until it becomes audible. Until it's not, if it's low, there would be some influence, some masking effect by these 2 noise signals on the tone. And the threshold of audibility would increase by that masking effect. And these narrowband noise maskers, they have a level of 50 dB. And with this 50 dB level, if you can imagine if they are very close to each other. So if the delta F gets close to 0, it's similar to the masking effect of the white noise, but here it's a narrowband noise signal, but it would have a strong masking effect. That means we go to very low delta F values. The threshold of audibility for the tone would be relatively high because it would be masked by the noise. If you increase the gap to a certain point, the effect starts to decrease because now the noise maskers are no longer at the same frequency as the test tone or too far away that they would influence the vibration on that position, which belongs to the 2 kilohertz tone, so much that it would be masked. And again, here we see that it's not a brick wall characteristic, but the wider the gap gets, the weaker the masking effect. If they would be very far apart of each other, you would reach the threshold in quiet, which would be somewhat a bit below 0 dB for a 2 kilohertz single tone in the threshold in quiet. If it would be not masked at all, the curve should at some point reach the minus, let's say, 2 dB and then stay there. And the closer the two noise maskers get to the tone, the stronger the masking effect. And that's what we see here. So here we see that until a certain frequency gap width, the masking effect is constant and then it starts decreasing. And that would again be an indication of the bandwidth, because if the noise maskers are outside of the same frequency region of where the sound is processed or where the sound influences the vibration with a characteristic frequency of 2 kilohertz, then there would be no much masking left. And if you repeat this kind of experiment for different tones with, again, noise, narrowband noise maskers placed around it, you could get then this bandwidth and then get the dependency of this bandwidth on the frequency. Is this clear? Yeah.
And I would assume if we increase the intensity of the narrowband noise, it will repeat, not repeat, but the level will also increase.
Yeah, exactly. The question was what would happen if we would increase this level of the masker. Like here we have the 50 dB and we see we are somewhat a little bit below 50 dB with the threshold of audibility. If we would increase this level to 60 dB, the curve would more or less shift up by 10 dB. Yeah, exactly.
Shouldn't it be 50 dB itself, like the level?
No, not necessarily, because it's just it can get audible even if it's not as strong as the other tone. Because if you have two tones which are equally loud, you would hear them quite clearly already. But here it's a noise masker. This noise has quite a strong masking effect. That's why it's only, let's say, maybe 4 dB below that it starts to become audible, but it doesn't need to be exactly the same level. But let's say the difference in level, in dB level, would be about the same if you would increase the level. Let's say if this would be 46 in this experiment, and if you would increase this level to 60 dB, it would probably go to 56. So this threshold would go up by 10 dB.
Because when we were looking at the plots for the masking in the beginning, like there was a single tone, right?
Mm-hmm.
So they're exactly at that level.
We had the white noise maskers first, but for white noise there was only the intensity given, because if you have a high bandwidth, the power itself depends on the bandwidth. And here, since it's narrowband noise, you can specify the level of the noise. And let's say if you would increase the bandwidth here, it would not have much impact on the masking effect because it's too far away. Then the curve would not go up, but the level of the masker would go up because you would energy in this frequency region. So the masker power would increase, but masking threshold would not increase. But if you leave the frequency settings the same, the bandwidth the same, then it would increase the density so that you get to a total level of 60 dB, then it would increase in this case.
I have a question from the previous slide.
Okay.
Sorry to this.
Yeah.
So there's a number of test tones and also the frequency difference.
The band, this delta FG is always the bandwidth. This is the difference between the highest and the lowest of these tones.
And also there's number of test tones.
Yeah.
Like,
but they're always spaced by 20 hertz. That means this frequency, this delta FG should be always the number -1 times 20. So they are connected, those two curves. You see here 1, and you have a bandwidth of 0. You have 2, and you have 20. 2 minus 1 times 20. 5 minus 1, this should then be somewhat like here in between, like 80, and 10 should be 180, and so on. So that's the connection between the number of tones and the bandwidth.
Okay. Can you tell me if we put like same tone twice, like with 0 difference?
Yeah, but then
so how can I find it on the graph?
If you would just have the same tone with the same frequency,
yeah, but two tones.
Yeah, but then,
tone, but
then it's only one tone. And you doubled the energy.
Yeah.
But then it would be the same because you increase it by 3 dB. But then again, it wouldn't be just need half the amplitude. So of course, there you would go up by 6 dB. If you double the amplitude of a tone, of one single tone, it would increase by 6 dB, but it would not, the bandwidth would not change. Okay, so you could again say it's one tone, and it has, this one tone has again the same level when it becomes audible.
Okay, so just like total, like it is the number of extra tones we are adding on
the total number of tones. It means one is only one tone.
Okay.
And if you have a single tone, you can say it has a bandwidth of 0 because it's a delta in its spectrum is just a delta function. If you have two tones, one in 920 hertz and the other one in 940 hertz, the total frequency range covered by those two tones would be 20 hertz. That's basically what we see here. The frequency range covered by the tones is then 20 hertz because you have 20 hertz distance between the tones. Okay, is it clear so far? Yeah. So then this was clear. There's another experiment. This might go faster to explain because it's very similar, but here they turned it around. The combination, they had the masker were tones, sinusoidal tones, again symmetrically spaced around 2 kilohertz, and the test signal was a very narrow band noise, which was increased in its level until it became audible. So now, if the level of the test signal was very low, people would just hear 2 tones. And they were asked if they would hear some additional noise or something else which makes it sound not that clean anymore. And then they changed the different distance between the 2 tones and checked the threshold of audibility of that narrowband noise signal. And again, you see basically the same tendency that the threshold of audibility for this noise test signal is more or less constant until a certain point, and then it starts decreasing. It's basically the same when the distance between the tones and the noise is getting too large, it would not be masked anymore, or not that strongly anymore, and that's why the threshold goes down, the threshold of audibility. It's also clear, but you see here the level relations are quite a bit different. We have the sum energy or power of the 2 tones gives a level of 50 dB, and this narrowband noise becomes audible already at something like 32 dB. It means the tones have much weaker masking effect on noise. Maybe you can imagine that if you have a clean tone and there's some noise, that you are much more sensitive to that noise, which is kind of really steady, and narrowband noise is kind of fluctuating, and that this kind of distortion-like sound is much more easily audible for us than in the other way around, when we have some maybe more or less annoying signal, kind of a noise-like signal, and then we are asked if we hear a tone within this noise. So the level relations are quite different, but the frequency behavior or spectral behavior is more or less the same, that if the distance of the tones gets beyond a certain threshold, the masking effect on that test signal in between is decreasing. Then in previous years, I explained more or less all of the methods, but it was a bit boring. So here I just have a little bit of a summary of what other experiments can be found in the literature. The one is a bit connected to that question, to your question before about phase, in phase and out of phase. But this was then measured with signal which were amplitude modulated or frequency modulated. And if you ask people if they can hear differences between an amplitude modulated and a frequency modulated signal, this is related to phase, and also phase differences can only be observed as kind of fluctuations or beating effects as long as they are in the same frequency region, that the basilar membrane vibration at that point is influenced by the tones, so that you see the beating. If you have two tones which are spaced more further apart, then each tone has just a constant amplitude, and you would not see that over or superposition of the two vibrations anymore. And this is then the effect where phase would matter. Mm. So this was one experiment for that. You can also do experiments with the loudness dependency on how much the loudness of a narrowband noise depends on its bandwidth. And you can imagine if you increase the bandwidth of a tone, it would be perceived within one band. This is different than if you increase the bandwidth so far that the different frequency components are not jointly processed anymore. And you can then ask people which tones are equally loud, which is always difficult to judge, but with enough listeners, you can get kind of some statistics in average. And you can see that there's also a relation between this loudness dependency and the bandwidth. And you see also data, you get data which supports the other experiments. At very high frequencies, they use tone bursts, which differ in frequency, and they present them to both ears. And they were trying to find out if the differences are audible. And also the detectability of time difference, if you have shifted signals in time shifted against each other, two tone bursts at different frequencies. This also strongly, the detectability of the time difference strongly decreases when the frequency difference of these tone bursts is equal to the critical bandwidth. That CB is the abbreviation for this so-called critical bandwidth, which is then kind of the measure of the frequency bandwidth in which signals are jointly processed or jointly influence the vibration of the basilar membrane. With all these additional experiments, you can say, well, there's a relatively good correspondence of the different methods. but you can't apply all methods in all frequency regions. So that's why they tried different ones and checked if they would correspond well enough. But from all these experiments, a dependency was found of or a connection between frequency and bandwidth. And this is the function here, the definition also of the critical bandwidth is this, that within a critical bandwidth, which is not a distinct band, but if some tones are jointly within a certain distance, which is smaller than this critical bandwidth, they would be would jointly influence the audibility of those tones. And this is the connection between frequency and critical bandwidth. And critical bandwidth is more or less the name of this phenomenon, that there is this critical bandwidth. And this is then the connection of that bandwidth and the frequency. And you see that it stays first relatively constant at very low frequencies, and then it increases at higher frequencies. And sometimes this is approximated by this curve, which is shown as the dashed line, which is constant until 500 Hertz. And then it goes up proportional to frequency with a factor of 0.2. But there are also formulas which approximate this curve a bit better, which I will show you next. So this is the one I normally remember. The other ones I have to look up. So I wouldn't ask you to know that from heart, but know that there are curve functions describing the critical bandwidth. But this one I would more or less expect that you can remember that the critical bandwidth is more or less constant below 500 Hertz, but and goes up proportionally to the frequency above that. So this is the rule of thumb, let's say, and this is a formula which is a bit more accurate and describes the curve a bit better. So, and the critical bandwidth is a unit, is also used as, or was introduced as a unit, and this unit was then called 1 bar. That means if you are at a frequency of 1 kilohertz, and if you go with this formula with this rule of thumb, we would say 0.2 times 1 kilohertz is 200 Hertz. It means 1 bar at 1 kilohertz would mean it's a bandwidth of 200 Hertz. If it would be at 500 Hertz, it would be about approximately 100 Hertz. If you would go to 2 kilohertz, it would be approximately 400 Hertz. So that is then the unit of a 1 bar. And you can also this is actually the bar bandwidth, or the critical bandwidth in Hertz, and with this approximation formula. And this is a formula for which we will see the curve later. So there's the bar scale introduced, which is a nonlinear mapping of the frequency scale, so that 1 bar has on that frequency scale always the same width. It means that is kind of a frequency scale meaningful for perception. And that bar scale, of course, must be the steps used for generating this bar scale must be quite narrow at low frequencies and must get wider at high frequencies. And that's basically what we see here, that this set value, which is then measured in bar, is can then be obtained with this formula. But the actual bandwidth in Hertz would be this formula. And additionally, you can find in the literature quite a range of other formulas describing the bar scale or the critical bandwidth dependency on frequency. But let's look at the bar scale. And this would be a curve like this if you connect all these dots we have here. These dots are just the steps going through in one, always going from in one bark steps. And if you go in one bark step at the beginning, you should do steps of about 100 hertz, right? So if you go here from 0 to 1 bark, it should be approximately 100 hertz. Here's another 100, and as we saw, the curve is not that close to that rule of thumb formula, but you would. But on the other hand, we have here a logarithmic scale. That's why we also don't see that it's always a constant step in x direction. But the further up we go, if we increase, if we go 1 bark further, we must cover a wider frequency range. That means we have to go more to the right. And that's why this curve gets flatter the further we come to the end. And this curve shows that the total bandwidth, if we go really up to 24 kilohertz, normally we say we can hear up to this would be 16 kilohertz. We are ending up at 24 bark. If you go to 20 kilohertz, it would be about 25. So this would be good to know that we can describe the frequency range of the auditory system, the audibility range or hearing range, as I called it before. This would be covered by 24 bark or 25, depending on how far you go. But this also has a large danger, because I often hear, or people often think, that the auditory system has 24 filters, which are next to each other, for each covering as 1 bark of frequencies. But this is not true. We saw that on the basilar membrane. It's a mechanical, continuous membrane. And if you go half a step wider, then you would still have a certain bandwidth around this frequency, but it's not one band of which is analyzed separately, completely from the other things, but it's just a region of frequencies which would be covered around that certain frequency. So the auditory system can be described with a bark scale, with bark values going up to 24 or 25, but it's a continuous, you can say, analog system, which is space continuous and also frequency continuous. And these dots here are just illustrating the steps going in barks, if you would go from bark 1 bark to 2 and so on. But in between you have also positions, of course, on the basilar membrane, which correspond to these characteristic frequencies, have the characteristic frequencies there. But it's nice to illustrate this frequency dependency of the bandwidth. By this, it doesn't show the bandwidth, that's what we saw before, but you see now how you have to map the frequency scale to get to the bark scale. And the bark scale has some nice properties, which we will also see later. But some of them are already shown on the next slide. Or are there questions regarding that?
I'm not so sure. So this frequency is the center frequency or the bandwidth?
No, this is a frequency mapping. Like if you would go from a linear scale on any for any measure to a log scale, you would have to draw a log function where you get the input and the output. X would be the input, and if you have a log function, you would get the output of that log scale, which you would then use as the new x-axis. And that's exactly what this is for. So you take a value here, go up, look and check where you hit the curve, and then you get the corresponding bark value. This is nothing else than this nonlinear mapping. Here is of course, here is the log scale in frequency. As it would get much wider, you wouldn't see here. Here it would go up more or less vertically, and then you would have very wide steps, because here that would be, if you look here, that would be 4 kilohertz going from 23 to 24, and here it's about 100 hertz. That could not be illustrated so well. That's why here we have 2 nonlinear scales mapped on this graph. So you have the log frequency scale here and the Bach scale here. But you could also, with the formula we saw before, you can put in a frequency. In this case, you would have to put the number of kilohertz, and you get the Bach value out. So that would be more or less, these are what we saw are points on this curve. If you plot this function on and then put f in log scale again, then you would get this graph from as we saw it here. And if you would connect the points, you would get the curve.
Is it like the fitting the beach kind of?
It's connected, and it comes on the next slide. There are comparisons of the Bach scale and the cochlea itself. We know the lowest frequencies are at the apex or helicotrema. There would be the vibrations of the lowest frequencies, and the vibrations of the highest frequencies would be close to the oval window or close to the base. And so here they measure not the distance from the oval window, but the distance from the helicotrema in millimeters. I think I mentioned before that the human cochlea has, if you go along the spiral, or if you could unroll it, but you can't, but if you go along the spiral, it would be a total length of 32 millimeters. And here we see frequency. We see that here it's again this nonlinear mapping. Here we have 100 hertz in this distance, and if you go in this distance here, it would be something like 3 kilohertz or something like that. So that's this nonlinear mapping from frequency. And the Bach scale, it's also called critical band rate. This Z value, which we saw before, is here. Here we see the values from 0 to 24 Bach, and you see that they are more or less equally spaced. And it means that 1 Bach corresponds to a certain length on the basilar membrane or within the cochlea. And this is quite proportional to that. And there are other methods, other scales here. One is the number of steps. When you say what kind of frequencies differences can you detect, if you put that next to each other, this is also kind of a relative scale mostly. And this is quite similar to the Bach scale, or proportional to the Bach scale. You would say, well, I have a tone and I change the second frequency of the second tone until it can be detected that it has a different frequency. You always have to play them sequentially, of course, not simultaneously. You play one tone, the other tone, and you increase the frequency of one of the tones, and until some people say now they have different frequencies, and then you take that one and do it again with another tone which is above, and then you would say that's a certain number of steps, and this would be then this curve. And this is relatively close to the so-called Mel scale, which is also called ratio pitch. And this is to how we perceive the pitch. That means the frequency height of a tone. And this is described by the so-called Mel scale. And this is, as you see here, also quite proportional. It's about a factor of 1. Here in this graph, it's exactly a factor of 100 between the ratio pitch and the Bach scale. So different scales related to auditory perception in completely different meanings are still quite close to each other, or proportional to close to each other. Yeah, but as mentioned before, the Bach scale is not the only one scale used for perception and also masking and effects and so on. This was generated by the school from Munich, Professor Zwicker. We have a meeting room here at IIS. Probably some of you know that there's a room called Zwicker, named after him. And another measure was generated by different experiments. Not too different, but the evaluation was different from what we saw before. And this is the so-called ERB scale. I will explain what this means. And here, people tried to find directly the frequency responses. The previous experiments just wanted to find kind of this edge point and call this the critical bandwidth. And here, people did experiments with, again, masking experiments, where they had a more or less a white noise signal, which had a notch in it, just a gap in the noise. And in between, in the middle of this gap, was a test signal, and the audibility threshold of that test signal was obtained by changing this distance or the width of that gap. You can imagine if there's no gap, then you should get the same effect as the masking of white noise, as we saw it before. So you would have a very strong masking effect. If you have a small gap, it would be still quite, the masking effect would be still quite strong. And if you now assume that the auditory system around the point of that characteristic frequency of the tone of the test signal would have a kind of a bandpass characteristic, how much the vibration of the point corresponding to that characteristic frequency of the tone would be influenced by neighboring other frequency components. And if that would be a kind of a bandpass characteristic, they assumed that would be a kind of bandpass characteristic, like this curve, what we see here. And if we have some noise, then, and we want to find out how much energy comes out of that filter, if that would be just a LTI, linear time invariant filter, we could apply signal processing, or I don't know if it's in statistical signal processing or in which lectures it's covered. If you have linear filters, linear time invariant filters and noise signals, you can get the power of the output of the filter by multiplying the content of the noise and the frequent magnitude response, or power spectral density you would have to use. And then you can calculate by that what comes out. The result would be the power of the signal which at the output. And you can also calculate it here. If this would be this squared magnitude response, and this would be the noise, then the power of the signal which comes out of the filter would be this shaded area. On both sides, you get some contribution, and the total power at the output would be this corresponding to that area. And you can imagine the smaller the gap gets, the higher the power, and the higher the power, the more vibration on the basilar membrane at that point of where the tone should become audible or detectable by the auditory system. The the masking effect would be even the strongest, the more vibration you have on that point. And so they made masking experiments and calculated the masking threshold independency of the width of this gap. And from this masking threshold, you could, if you assume that a certain power difference is required to become audible for the tone, or the relative amplitude of the tone with respect to the influence of the noise would always have the same ratio, would need the same ratio, then you can deduct from the masking threshold, you can calculate backwards to find the frequency response of that filter. So basically that's what they did with different center frequency or tone frequencies and notch frequencies. And where's my mouse here? With different center frequencies and different notch widths and so on. And by that, they obtained, in this case, one example is given here, for a frequency of 1 kilohertz, they obtained a frequency response curve, which looks like this. That's what they got, because the noise is always symmetrically spaced around the center frequency. You can only get symmetric curves. This must not be, is not necessarily fits perfectly with the auditory system, but it's quite a good approximation. And that would then be a frequency response, and you can approximate those frequency responses with enough experiments at different frequencies. And then they do the next step to calculate the so-called equivalent rectangular bandwidth. For that, I will maybe draw something like that on the board. And maybe you can give me feedback if you can see it or if it's too dark, if you have too much of the screen on the in the camera. The board might be a bit dark. So then I could zoom in a bit further. Let's assume, we don't need it. We have our frequency response, which comes out of the measurement. So this would be the h of f, or we take this absolute value and square it, and we have such a function, which looks like this. We want to find another function which has the same center, which is rectangular function, which has the same height as the function, and the area between the two curves should be the same. So then we would have to go up somewhere. What is missing on one side should what is missing here should be, probably we would have to go a bit further out, like here. So what is missing here should be covered here. So these two areas are the same, and on this side maybe like this, and then we would have a curve like this. And these two curves should have the same area. So that means if there would be white noise, would be fed through such a filter, to the green filter. So maybe I should correctly describe also what we see. This is the frequency, of course. Let's say the power of the output signal when we feed white noise through such a filter would be the same. And that would then be, we can then calculate the width of this rectangle. And this is then called the equivalent rectangular bandwidth. And this is abbreviated as ERB. I think I have a sketch of that also in the lecture notes. Yeah, it's maybe a bit nicer than my drawing here. But I hope the idea is clear that the height is the same, and the area below the curve should be the same. And then we get, for depending on the filter characteristic, we get this equivalent rectangular bandwidth. And that's what they calculate. Here is again described in words. And that's all what I already said. And from their experiments, they got a curve which shows the equivalent rectangular bandwidth in hertz. That means if you take this, because we have a frequency scale here, this would be then given in hertz, and its width again would depend on its center frequency. And if we put in the center frequency and calculate the bandwidth, then we can use this formula for calculating the equivalent rectangular bandwidth depending on the frequency itself, on the center frequency. And this is similar to the critical bandwidth, what we saw before, but as I said before, it's calculated or derived a bit differently, and that's why it's also giving a slightly different, or quite some different frequency dependency. So we'll look at that. And again, from that width, you can do similar thing as with the Bark scale. You can map to a frequency where one ERB width is constant, as we did with this critical bandwidth and the mapping to the Bark scale. Here, that's a bit more complicated. It's the name is more complicated. It's called ERB number. And this would then be the function describing mapping from frequency to this other frequency scale, which has constant ERB, let's say. And now let's look at this curve which comes out from this. And that is actually shown here. So in their publication or in the book of one of the let's say people who introduced this ERB scale was a professor from England, Brian Moore, and they had published this curve here, which is the solid line, and they support their results with other results from different other researchers and experiments to show that this is quite a good approximation, but depending on what you actually want to measure. And the dotted line is the Bark or the critical bandwidth, depending on the center frequency. And so you see that there's quite some difference. So the ERB scale is generally a bit lower. That means the bandwidth you get there with this measurement they are more narrow than the critical bands, critical bandwidth from Zwicker. And also at very low frequencies, they don't have this tendency to get almost constant, but they still decrease to very low frequencies. But both of them are used in perceptual models. In perceptual audio coding, we come to the models, to some models for that. Data traditionally there's more frequently the Bark scale on the critical bandwidth is used. This also takes into account that if you want to control the coder with a certain frequency resolution, you also have to take into account the site information and take the whole efficiency of the whole system into account. And that's why often the Bark scale is quite okay for doing that. But other models are often built on top of this ERB scale. But I hope it became clear how it is derived, and that it's also well motivated, this other scale. And the next part, we will address gamma tone filter banks as a means of approximating, of building a first model of this the basilar membrane vibrations, let's say, by linear filters directly, and this is most frequently based on the ERB scale. Okay, but now maybe I should conclude this part, or are there questions?